Assalamu alaikum. Welcome to another lecture of W434. We are studying the power electronic devices that are used as switches for power electronic circuits. So far, we have discussed the diode, the SCR, and in today's class, we shall see the most common and the most widely used power semiconductor device in low power application and up to a medium power application, that is known as a MOSFET. So let us start with our topic on MOSFET. MOSFET is an abbreviation of metal oxide semiconductor field effect transistor. You might have studied this in your first course on electronics, electronic devices and circuits. Therefore, we shall not dig deep into the working and operation of a MOSFET. However, we would like to see some of the aspects which are really very important to understand the concepts of power electronics. It is a three-terminal device. It is a three-terminal device. It is a unipolar device because current flow is only either due to the holes or due to the electrons. The current flow through an FET is controlled by an electric field which is set up by some externally applied voltages. So let us see how a MOSFET actually works and what is the procedure and what are the important things with respect to the MOSFET for this particular course. So it is a voltage control device such that we have a gate terminal. This is a symbol here. We have a drain here. This is the source, and here we have the gate. So it is a voltage control device such that the voltage from gate to source should be greater than the minimum voltage required to bring this device in the conduction mode. Because of the inherent characteristics, there is a body diode that comes automatically while the MOSFET is constructed. You can read much about this body diode and the internal construction of a MOSFET in the electronic books. Typically, they are available up to 600 ampere and 1500 volt rating. They are available, and they are also available in high current and low voltage application. For example, Semicron has manufactured a MOSFET that is able to work at 60 volt but can carry a current of 1000 ampere. MOSFET is able to block the positive voltage such that, for instance, if we have this MOSFET, if no gate to source voltage is applied in this particular MOSFET, if we do not apply any gate to source voltage, then it is able to block the positive voltage applied between the drain and the source. So it is able to block the positive voltage, and if we apply the gate pulse, then a current flows from the drain to the source. Thus, it is a device which of allowing the current to flow in the forward direction. As far as the reverse voltage is concerned, because of the body diode which is connected in an anti-parallel configuration here, you can see here this configuration is known as an anti-parallel configuration because because this diode do not allow the current to flow when this MOSFET is turned on, and therefore despite that it is connected in parallel, we call it an anti-parallel device because both of them work under different circumstances. So you see, if you apply a positive terminal here and a negative terminal here, these body diodes get forward biased, and therefore this device is not able to block the negative voltage. However, if when we apply this positive voltage here and a negative voltage here, then the current flows from the source to the drain via this body diode, and therefore a negative current is also possible through this particular device, and therefore this whole device is capable of working in these two coordinates. So previously we have seen that an SCR is able to block positive voltage and the negative voltage, but the current was unidirectional. However, this MOSFET, because of the presence of this body diode is able to conduct the current in both the forward direction and in the reverse direction. However, it is only able to block the voltage in the positive direction. Let us move ahead a little bit. Now, considering this body diode that we have shown here, this body diode may be of an inferior switching speed compared to this particular transistor, because this comes as a result of our configuration of our semiconductor material placement and its configuration. This body diodes comes as a free source. So sometimes it happens that this diode do not have a speed which is compatible with the speed of this particular MOSFET. In that particular case, there are some techniques where we disable this particular diode and we install a high frequency or high switching frequency diode in an anti-parallel configuration. For that, the circuit is quite simple. So you can see here, we have, suppose that we have this MOSFET, and here we have this body diode which is not fast enough to be compatible with this main device, which is the MOSFET. To block it, what we do is that we connect a diode here in series with the drain. Therefore, the addition of this diode do not permits the current to flow in the negative direction, because when the current will flow here, it cannot go further because this diode is reverse biased, and therefore the functioning of this body diode dB is effectively nullified by the placement of this blocking diode here. So to add the high switching frequency diode, the diode is connected, a new diode is connected in this particular configuration, and here this diode will carry the negative current when this transistor is turned off. So the device internal diode is disabled by connecting two diodes in the system, one that blocks the flow of current through this body diode, and the other one is that particular diode which has the same or the superior switching characteristics compared to this particular MOSFET. So this is how we can actually neutralize the body diode. Also, if you see here, MOSFET has two important limits that we shall see in the data sheet. There are two important limits for a safe operation of a MOSFET. The number one is the breakdown voltage from drain to source, and the second one is the VGS maximum, which is the maximum that can be applied from the gate to the source. This is the maximum voltage that can be applied. How can we actually create a system where we ensure that this device do not exceed this particular limit? This can be done by a very simple circuit, that is that for a particular MOSFET, we connect a Zener diode before the in parallel with the gate to source, and here we have the switching cycle or the switching signal that is applied. So Zener protection is applied such that we have VZ1 and we have VZ2, such that the Zener voltage sum VZ1 and VZ2 is always set less than the maximum gate to source voltage. So for instance, if this gate to source voltage is set at plus minus 20 volt, then you can actually use a Zener diode something around 15 to 18 volt rating, so that whenever there is a spike due to any malfunction or any circuit behavior, these two become short circuit and thus safeguard the gate terminal of the particular MOSFET. Also, if you notice here that MOSFET has power losses in a MOSFET. are a function of the gate to source current I square drain to source into RDS on. So whenever we turn on a MOSFET, there is a resistance which is offered by the channel of the MOSFET, which is known as the RDS on. For some of the MOSFETs, this is in several hundreds of milliohms, and some for them it is very low as few milliohms. And this IDS or IDS I square ds is the maximum amount of current that flows from the drain to the source. So as you will see shortly that the power losses of a MOSFET are less than the power losses across a diode. Also, if you notice here that this has a positive MOSFET has a positive temperature coefficient, which means that paralleling the MOSFETs is quite easy. Suppose that I have these two MOSFETs which are supposedly connected in parallel. So let us say that we have this is the source, and here we have the drain. Suppose that we have this is the RD, and here we have the RD, and this is the RG or the gating resistance, and here we are with this transistor. Let us say this is T2, this is T1. So let us say that for some temperature T, if RDS on of T2 rises and becomes greater than this T1, because when the temperature rises, this RDS on also rises. RDS on of T2 rises with some temperature value, then the T1, then the current through the T1 shall also rise, because now this one has a higher resistance, higher channel resistance, therefore more amount of current shall flow through this T1. So what happened here is when the current of T1 rises, then this will increase the temperature of the transistor T1. When the temperature of the transistor T1 rises, then the RDS on of T1 shall also rise. This will decrease the amount of current flowing through this T1, and more amount of current shall be diverted to the transistor T2. This will decrease the current, and hence there is always a thermal stabilization in a MOSFET circuit, and this is a big advantage over the diodes which have a negative temperature coefficient, and it is always a problem when we connect two diodes in parallel. So this is not a problem. Let me revise this again as well. Let us say that we have let me remove this as T1 and T2. Let us say this is Q1 and this is Q2. Let us say I Q1 let us say that the temperature of Q2 increases. This increase will make the RDS2 also increase. So therefore I2 will decrease, because these two devices are connected in parallel. As a result, this I1 shall increase. As this I1 will increase, it will increase the temperature TQ1. When this TQ1 increases, then the RDS1 shall also increase, thereby decreasing the amount of current I1 and diverting the amount of current I2. More current is diverted to current I2, and therefore by default, because of this positive temperature coefficient, this MOSFET has a thermal stabilization process in place that allows multiple devices to be connected in parallel without having a current sharing mechanism. Also, if you see here, MOSFETs gate inputs are highly capacitive with almost zero losses. So we have the capacitance available, that is the gate to source capacitance, CGS, right? And of course we have the stray inductances there as well. So therefore, in the presence of this gate capacitance and the stray inductance, there is an LC circuit that creates unwanted high frequency oscillations in the system. Therefore, to dampen these oscillations, a small resistance is usually added in series with the gate signals, with the gate connection, that acts as a damper to these particular oscillation. So that is why we have these resistances that are connected in series with the gate. So I hope you have enjoyed this particular lecture. So till the next lecture, take care. Allah Hafiz.